Today we have Rishabh, who will be talking about how to avoid fooling ourselves in deep RL research. Rishabh is a research assistant in the Google Brain team in Montreal. Previously, he was an AI resident in Jeff Hinton's team at Google Toronto. His research interests mainly revolve around deep reinforcement learning, often with the goal of making reinforcement learning methods suitable for real-world problems. He will talk with us about his work published at the NURI IPS in 2021, which received an Outstanding Paper Award, where we find that statistical issues have a large influence on reported results on widely used RL benchmarks. To help researchers do good and reliable science, he will discuss how reliably evaluate and report performance on he will discuss how to reliably evaluate and report performance on reinforcement learning and machine learning benchmarks, especially when using only a handful of runs. Please be advised the seminar is being recorded. Please have your video off and keep yourself on mute unless you have a question to raise. We also have the chat bar in the side, which I'll be monitoring throughout the seminar as well. So without further ado, Rishabh, go ahead.
Yeah, thanks for the introduction. Hi everyone, I'm Rishabh. I'm a research scientist in the Brain team. And today I'm going to talk about our work on deep reinforcement learning at the edge of the statistical precipice. This is based on a New York Studio and published paper. And for more details, you can actually check out the link, agarwal.io/reliable. Okay, so I guess let's get started. So before even jumping into the talk, what is this talk about? So this work calls for a change in how we evaluate performance on reinforcement learning benchmarks and machine learning benchmarks. And for doing so, we present more reliable protocols which are easily applicable, even if we have a handful of runs, to prevent unreliable results from stagnating the field. And it only requires a few lines of code for doing this evaluation. And you can check out this open source library, which has detailed instructions on how to use it. Okay, let's now go to the main presentation. Now, research in deep reinforcement learning relies on evaluating performance on a diverse suite of tasks versus progress. For example, if you look at the commonly used benchmarks, we have things like ProcGen, Atari 2600 games, or things like DeepMind Control Suite. Now, evaluating on a suite of tasks reveals the strengths and limitations of methods while simultaneously guiding researchers towards methods with promising results. So most published results before this work, and even I think now, on deep reinforcement learning benchmarks compare point estimates of aggregate performance, such as mean and median scores across tasks. Now, I'm just giving you examples of some of our own work before this paper, where we use point estimates to compare performance of different algorithms on, I think this is the Atari benchmarks. So you can see things like on distributional RL, offline RL, or this thing called SPR, but basically I didn't want to point fingers at anyone else. I'm just pointing to our own papers where we have used point estimates to make the case that these estimates are actually prevalent in deep RL research. Now, unfortunately, point estimates ignore the statistical uncertainty implied by the use of finite number of runs. What do I mean by that? Let's say you go out, repeat the experiment with, let's say, on a different hardware or different set of random seeds. It is quite likely that the point estimate you get of this mean or median score would be different. And this uncertainty or this sort of change in your point estimate is not really sort of reported if you just report a single point estimate. Now, furthermore, beginning with the arcade learning environment, there has been a shift towards computationally demanding benchmarks. And this has led to the practice of evaluating only a handful of runs per task, which exacerbates the statistical uncertainty in point estimates. So if you go back to the 1990s, you can see that we're using about 100 runs. While if you go after post ALE, you can see that most of the sort of well-known published papers in deep RL have used 5 or even less runs. Now, we can ask a simple question. So what could go wrong with ignoring the statistical uncertainty? Now, to illustrate the pitfalls arising from the naive use of point estimates in the few-run deep reinforcement learning regime, what we did for this work was we ran a case study on this benchmark called the Atari 100K benchmark, which is composed of 26 Atari games. Now, on this benchmark, algorithms are evaluated after 100K training steps, which roughly corresponds to 2 to 3 hours of gameplay. And this is the amount of time a human also needs to master these Atari games, sort of roughly. Now, on this benchmark, what has been typically done is we report aggregate human normalized performance across these 26 games. And for doing the score normalization, what we do is we compare the score on a scale so that a human is assigned a score of 1, while a random agent is assigned a score of 0. And our agent score is normalized so that it is on the similar scale. And you can see how the normalization is done. All right. Now, prior work on this benchmark has reported median normalized scores, which basically corresponds to the sample median over the per game mean scores, and has typically used 3 to 5 runs for computing these median scores. So let me just explain it a little bit further. So let's say you have 3 to 5 runs for each of the games. So now, when I say run, I basically mean a training run. Now, for each of the run, what you do is you get a number out or a score out. You compute the average score for each of the games. So if you have 26 games, you have these 26 numbers, and then you compute the sample median based on these 26 numbers. And that corresponds to your performance metric you have used on the benchmark. Now, for our case study, what we did was we evaluated 100 independent runs for 5 algorithms, which were representative of this benchmark back then, which includes DER, OTR, DRQ, curl, and SPR. And now, for most of these algorithms, we didn't even re-implement the code. We simply took the open source code released by the authors and simply evaluated the code for 100 independent training runs. Now, score for a run is the average returns over 100 evaluation episodes after training. So for each run, we get some sort of an expected return score. And now what we have is we have 26 games and we have 100 scores for each of the games. Now, assuming that these 100 runs capture the underlying distribution of scores for each of the games, we can subsample scores from these runs to investigate the statistical variations in the pure run routine. Which is, you can think of having access to these 100 runs, in some sense, give you access to the distribution of scores you would get. And now you can sample from this distribution to see what would happen if you have a, let's say, a smaller number of runs. Hopefully, so far so good. Any questions so far? I guess not. That's good. Okay, so the first question we asked was, what if I report performance using a different set of runs? So what you see on the screen is the reported median scores, which are shown by the dashed lines, which were reported in the publication with a fixed set of random seeds. And we said, well, what if we use a different set of random seeds and report the score? So what I'm showing here as distributions is, this is the distribution of the median scores if I were to use a different set of runs. Now, you can see that the sample medians, which are reported in the literature, exhibit substantial variability, which is the dashed line, or the reported scores do not really give you any indication whatsoever of this variability they really have. And they often severely overestimate or even sometimes underestimate, if you look at the case of DER, the expected median score. And there is actually a fairly large potential for drawing erroneous conclusions based on these point estimates alone. Furthermore, if you look at, I guess I can give you one example here. So if you look at the DER and the OTR algorithm, which corresponds to the blue and red lines respectively, in the literature, it was believed that DER is a worse algorithm than OTR. But when we did this distributional analysis, we did find that DER is actually a much better algorithm than OTR, because you can see that the distribution of DER is much further from the distribution of OTR, but their point estimates seem to be reported flipped in ranking in the literature. Okay, hopefully, I guess so far so good. Another interesting thing we did find was that the median of sample means is a biased estimate of the median of true task mean scores, which is, let's say, if I give you access to infinite runs or infinite training runs, you can compute the true expected score for each of the tasks, and then you compute the true median based on these true expected scores. Now, the thing you're actually computing is that you have a finite number of runs, you compute the average scores based on these finite number of runs, and you compute the median of this. Now, the expectation, if you repeat this process again and again, that expectation does not really match the true median score. Now, this is, I think, a well-known fact, and you can easily see why this is true from the equation below. But what was surprising or maybe interesting here, that the median, the bias in this median score we report can actually dominate the comparison between algorithms. And also, so one thing you can observe is, first of all, the bias is not in the same direction. For some algorithms, as we increase the number of runs, the median increases, while from some other algorithms like curl, as we increase the number of runs, the expected median or the median score we have decreases. And I guess I can just give you one stat. So it's the SPR, the improvement of SPR over DRQ, about 33% of that improvement really corresponds to the bias. So you can see that the bias can actually play a big role in if you report only a finite number of runs. And I guess maybe this is more to say, so we asked also the question, at least on this benchmark, how many runs do we really need for negligible uncertainty? Now, as we all know that if you claim improvements with 3 or even fewer runs, that may naturally raise eyebrows, but Hopism suggests that 20 or 30 runs are enough. Now, by calculating the 95% confidence intervals on sample medians, we find that this number is actually closer to 50 to 100 in Atari 100K. So for example, if you look at the SPR and the DRQ algorithm represented by the green and the orange line or yellow line in this slide, you can see that their confidence intervals still overlap, even if you use as much as, I think, 25 runs. And you need slightly more than that to be able to have like a statistically valid comparison. So, but this is actually far too many to be computationally feasible for most research projects. I saw a message in chat go by. Okay, sorry, that was something else. All right. And I guess finally, I just want to make this maybe somewhat orthogonal to the topic of this talk, but we should also not change the evaluation protocols when we are comparing to prior work, because that invalidates these comparisons. Now, what we are seeing here is actually we compare against, I think, 2 algorithms, namely Curl and Sunrise, which used alternative evaluation protocols involving maximum across the runs or maximum during the training, as opposed to reporting end performance results. And we find that on Atari 100K, that these 2 protocols produce substantially different results, which are of a magnitude greater than the actual difference in score. So what we did was Curl, for example, used, I think, maximum results found during training as opposed to reporting the final performance. And if we were to repeat the same procedure for the baseline algorithm, which was DER, we see that the performance of DER is much better than that of the reported performance of Curl, which is shown by the vertical dashed line here. And I think this also is the point of use of max. I guess max is problematic in the sense that when you're using max, in some sense, it becomes a part of your algorithm, which is if you have, let's say, 5 runs, and you're reporting the maximum result on the 5 runs, the max operation itself is a part of your algorithm. And in some sense, the total budget you use is 5 times the budget for each of the runs. And with this budget, you could have done something much better rather than doing this max operation. But maybe it's too much detail. I'm not going to be more detail in this talk, at least. Please refer to the paper if you want to know more about this result. Okay, so far I think I've convinced you that there is a problem. Now, the problem is that we have been reporting point estimate, reporting of point estimates. So the natural question to ask is, so how do we reliably evaluate performance? I guess I'll go through some of these solutions. So one of the common solutions proposed often is, well, why not just fix random seeds? So I'm going to argue that fixing random seeds is not really a solution. Why? So there are 2 reasons. Well, first of all, why should we prefer one set of seeds over another? Which is why should I use seeds 1, 2, 3 over seeds 4, 5, 6? Second, I think it's often we can't really fix randomness in practice. So for example, if you use JAX or TensorFlow, you can't really fix the randomness coming from GPU operations. Similarly, even if you use PyTorch, you can fix the random seeds. But if you go to use a different hardware, then again, there is no guarantee that you'll have fixed randomness. The plot here on the slide is showing basically, I think, correlation of 2 independent sets of 100 runs for each of the games with same set of random seeds, except you're not able to control the GPU randomness in JAX. And you can see the correlation is really small from, I think, 0.2 to 0.3. Okay, so what about evaluating more runs? Because I guess you have more data, you have less uncertainty. Now, evaluating more than a few runs is typically infeasible for the computationally demanding deep reinforcement learning benchmarks. And just to give you an example, if you do 5 runs on 50 Atari games for 200 million frames, it takes about 1,000 plus GPU days. And evaluating, I guess, more than 5 runs is going to even take more. And as we move towards more challenging and complex tunnel benchmarks, evaluating more than a handful of runs will become increasingly demanding due to the increased amount of compute and data needed to tackle such tasks. Okay, so I guess we have to change the question now. Rather than saying how to reliably evaluate performance, the question becomes, okay, how to reliably evaluate performance with a handful of runs? So is statistical significance testing the solution? I guess somewhat controversially, I'm going to say that at least we don't think so in this work. And the reason for this is that statistical tests are one of the reasons is their dichotomous nature, which is they only care about significance versus not significant, and common misinterpretations. There's lack of statistically significant results does not demonstrate the absence of effect. And given enough data, any trivial effect can be statistically significant, but may not be practically significant. Furthermore, they often hide effect sizes, such as the size of improvement over baseline, and only report whether the result is significant or not. Now, just to give you a fun fact, the main statistics journal in the USA actually bans threshold and p-values to avoid the misuse of these statistical significance tests. So in this work, we are saying, well, we're not going to use statistical significance tests because of all these issues. Instead, what we are emphasizing is using statistical thinking, which is any performance estimate based on a finite number of runs is a random variable. And I think all of you know that. But what we are saying is that we should also treat it as such. I think there's a cheeky meme on this slide showing how we do things in normal science versus how do we things in machine learning. Anyways, so in this work, what we do is we provide 3 tools for reliable evaluation aligned with the principle of reporting statistical uncertainty in results. Now, these tools are actually generally applicable for any machine learning benchmark where performance across different tasks is aggregated. I'll walk through these tools one by one in this talk, but just to give you a summary of these tools. So first of the tool is how do we report uncertainty in aggregate performance? For that, instead of using point estimates, we argue for reporting interval estimates. Now, let's just jump to that maybe. So instead of point estimates, we report reporting interval estimates via stratified bootstrap confidence intervals. Now, these confidence intervals are simply answering the question, if we repeat the experiment with different runs, or let's say random seeds, what aggregate score or performance are we expected to get? So it's simply answering this question about, okay, what is the uncertainty we have in our results if we were to repeat our experiments? And the way these intervals work is that we resample runs with replacement independently for each of the tasks. And in this way, we basically come up with a sort of a distribution of scores. And using that distribution, we compute the 95% bootstrap CS. Hopefully, maybe the animation makes it clear how the resampling process happens and why it's slightly different from why the stratified word, where the stratified words come from. Now, one thing I'd like to point out is that if you only have, let's say, a single task with n runs, you only have n random samples, and bootstrapping CIs may not even make sense if you have n less than 5. But if you have m tasks with n runs, you have a total of n times m random samples. So let's say if you think about the Atari benchmark, you have 26 games, and with 3 to 5 runs, you have about, let's say, 70 to, I think, 100 plus samples. And now bootstrapping results in reasonably accurate CIs, even with a small number of runs, because you have multiple tasks. So in some sense, you're aggregating information across all the tasks, and that is giving you more confidence in your results. Okay, so this was the thing about how to put like a good alternative for point estimate. Now, other thing I want to talk about is the variability in performance. Now, most deep reinforcement learning benchmarks yield scores that vary widely between individual runs and tasks. Now, aggregate metrics such as mean and median paint an incomplete picture as they conceal this variability in performance. So if you look at the animation here, what you're seeing is all these different sort of data sets have different distributions or on both the x coordinates and the y coordinates, but their aggregate statistics such as the mean and the standard deviation, as well as the correlation is the same. So basically these aggregate, if you were to only look at aggregate metrics, you would not realize that the distribution of individual points is very different for all of these graphs. Okay, so how do we tackle this problem right now? Right now we use tables with per task mean scores. Now, they can reveal such variability, but these tables are often overwhelming for comparing algorithms beyond a small number of tasks. Furthermore, standard deviations are frequently omitted from such tables because of things like space constraint, I think. And mean scores sort of present an incomplete picture for multimodal or heavy-tail distributions. So there are a bunch of issues with these sort of the current reporting. And I guess these tables also we don't have enough space in our papers, so these tables often end up going to the appendix. Now, instead of tables with per task mean scores, what we recommend is a tool from computer science called performance profiles with stratified bootstrap confidence bands. Now, performance profiles are simply basically plotting the distribution of all the scores across all the runs and tasks. And basically, you can see if you look at the equation here, it is simply the tail distribution, or 1 minus CDF of the distribution of all the scores you get across all the runs in tasks. Now, these profiles are typically used for comparing solve times of different optimization methods, and they have some nice properties because they are robust to outlier runs in tasks, and they're also robust to small changes in performance across all tasks. Now, I guess it might be easier to understand what these profiles look like if you were to plot them. So here I'm plotting these profiles for the Atari 100K benchmark. As I said earlier, these profiles show the tail distribution, or the 1 minus cumulative distribution of the scores on runs combined across all the tasks. Now, the nice thing about these profiles is that they allow for qualitative comparisons at a glance. So, for example, if you can, the area under the curve actually corresponds to the mean score, while if you can also read any sort of percentile from the y-axis. If you draw a line, let's say at horizontal line at y equal to 0.5, the place where these curves intersect, y equal to 0.5, corresponds to the median score. And there's also a thing called, if one curve is above another in such profiles, then this corresponds to stochastic dominance, which is a way to combine, or which is a partial ordering for random variables. Now, as I said earlier, we can also read any score percentile from such profiles. So if you want to look, let's say, the bottom percentile or the top percentile, you can simply glean that from this profile. Another way to read these profiles is you can also ask the question of how many runs achieve a score greater than a certain human normalized score or certain score. For example, in this slide, I think I'm showing how many runs are higher than a human normalized score of 0.5. So what do? You just draw a vertical line at that sort of coordinate, and you just check, okay, on the y-axis, what is the fraction of runs which do this? So if you look at, I guess here I'm talking about the simple algorithm or the DR algorithm, and I see around 25% of the runs score higher than 0.5 human normalized scores. So, like, I think overall, what I'm trying to say is that these profiles are a good tool for qualitative summarization, and they tell you the entire distribution of scores across all the runs and tasks. Now, they're great for qualitative comparisons. Such profiles often intersect at multiple points, as most algorithms do not strictly dominate other algorithms. So I guess it is inevitable that if you have, let's say, a new algorithm, it is likely to outperform previous algorithms on like a lot of tasks, but maybe underperform these algorithms on some of these tasks. And because of that, it is likely that the profiles would intersect. Now, this makes it harder to say, okay, which algorithm is better than which algorithms, because they both have some sort of pros and cons. And we still need aggregate metrics for reporting quantitative improvements. So, or at least doing finer comparisons require these aggregate metrics. So let's talk about these aggregate metrics now. Now, existing metrics are in some way flawed. Mean is prone to outlier performance, which is if you have, let's say, a few outlier tasks, mean performance can be mostly dominated by those things, while median is unaffected by zero scores on nearly half of the tasks and is statistically inefficient. So I guess let me repeat the previous point again. If you are measuring the median score, which is, I think, the common way of reporting results in R, if you get a score of 0 on half of the tasks, your median score wouldn't change. So what we really need is better metrics that are not unduly affected by performance on outlier tasks, have small uncertainty in results, even with a handful of runs, so that we can make comparisons easily, and are much more robust indicators of performance. So in this work, we do recommend alternative metrics based on robust statistics, including interquartile mean and optimality gap. And both of these metrics can actually be read as areas under the performance profiles I presented earlier. So interquartile mean is basically something called, I think, 25% trim mean across all the runs. So it is something like in between median and mean. Mean is, I think, 0% trim mean, while median is 50% trim mean, which is you trim almost all the data, while in median you do not, or in mean you do not trim any of the data. While in IQM, you trim 25% of the outliers on both sides and take the average of the middle 50% of scores on all the runs. So maybe okay, and optimality gap measures how far from optimal your performance is on all the tasks, as opposed to, I think, if you're measuring mean performance. That's it. No metric is perfect. We are just presenting better alternatives for existing metrics we use in practice. Now, just to maybe give you some clarification about what is IQM. So interquartile mean, or IQM, corresponds to the mean score on the middle 50% of the runs combined across all tasks. And I guess you can see this animation to see how IQM is computed. So we get the scores for each of the individual tasks, sort them, and then you just take the mean of the middle 50% of the runs. Now, compared to mean, interquartile mean is robust to outliers, and compared to median, it is a better indicator of overall performance and results in smaller CIs and require much fewer runs to claim improvements. So I guess if you look at this plot, you can clearly see that the confidence intervals of the IQM is much smaller than that of the median. And now another metric we also suggest is called probability of improvement, or something I like to say, like this metric directly asks the question of, am I better than the baseline? Like often in machine learning and reinforcement learning, one of the kind of comparisons we want to do is we want to ask whether the proposed algorithm is better than the existing algorithms. So if you want to really just measure how likely the improvement over baseline is, irrespective of its size, you can use this metric called probability of improvement. And this metric is quite useful for head-to-head comparisons. Note that although this metric ignores the size of the improvement, which is even if you get, let's say if you get 1% improvement or 100% improvement, the metric is going to report that the probability of improvement is 1. And just to give you a little bit detail about how this metric is computed, this is actually based on the U statistic of a man-whitney U test. Maybe these are complicated words. Easy way to think about it is if you have a bunch of samples for 2 different tasks, you just do all pairwise comparisons, and then you just take the average where the algorithm X is greater than Y, you assign a score of 1. If the score of X is same as score of Y, you assign a score of 0.5. And if the X is less than Y, you assign a score of 0, and you just average out all these scores. And that's how you get a probability of improvement on a given task. And then you average it over multiple tasks. Okay, so far so good. So I guess I covered a lot of these metrics and things. Maybe I forgot. So what we did in this work was we said, oh, we can use the recommended tools for reliable evaluation. And we did that actually in this work. And we scrutinized performance evaluation on existing algorithms on other widely used RL benchmarks, including the arcade learning environment, ProgGen, and the DeepMind control suite, which again revealed discrepancies in prior comparisons. So I guess one thing which we often do in arcade learning environment results is to report the sample efficiency curves. I guess here you might be, or at least you might be familiar with some of the algorithms reported in the slide. So the first thing we note here is that the interval estimates of median scores are visibly much larger compared to that of IQM and strikingly overlap for certain methods. And furthermore, depending on the choice of the metric, the ordering between the algorithms changes. So for example, if you compare the rainbow and the IQN algorithm, you can see that the ordering has flipped from going from median to IQN. And I guess the inconsistency in ranking across aggregate metrics arise from the fact that such metrics only capture a specific aspect of overall performance across tasks and run. I guess another thing we did was to report these interval estimates, and I guess I can just focus on one cool fact here. So if you look at the median or IQM, you can see as like we have made progress. So I'm listing newer algorithms on the top and older algorithms at the bottom. We have been getting better at median and IQM, but if you look at optimality gap, there is a flip in ranking. Lower optimality gap is better because an optimality gap of 0 means you're as good as a human on all the games, while optimality gap of 1 corresponds to a random agent. So lower optimality gap is good, while higher median, IQM, and mean are good. So you can see that we are improving in median or IQM scores, but we're getting worse in terms of optimality gap or how far we are from human performance. And this might have resulted from the focus we have on median as opposed to any other metric when we're comparing algorithms on the Atari benchmark. And also, I guess one more thing you can easily see is mean is pretty much dominated by the outlier task, because you can see that IQM gets a score around 2, while if you look at Dreamer V2, the mean performance is around 10. And the reason for that is that on the game of James Bond, Dreamer V2 gets a score, I think, of 50 or higher. And that's why the mean tends to be dominated by some of these games. And I guess since performance profiles will capture the full picture, they would often illustrate why such inconsistencies exist. So I guess it's not possible to do this here, but if you squint hard enough at these profiles, you'll see why there is this flip in ranking happens and why these sort of inconsistencies exist. All right, I guess. We also computed this probability of improvement on the ProgGen benchmark. So what I'm showing you here is that algorithm X on the left claimed improvement over algorithm Y in their published paper. So we said, okay, let's just measure what is the probability that algorithm X indeed is an improvement or over algorithm Y. And surprisingly, we find that some of the collective improvements are only 50 to 70% likely, while some of the improvements are not even actually improvements. So if you compare, for example, things like UCB direct to PLR, we see that that's actually not even an improvement, while other improvements are really small. Like I think, for example, PLR over mixed edge or UCB direct over mixed edge. And finally, I think we again do this sort of analysis on the DM control benchmark on the 100K and 500K stuff benchmark on DM control. And we found that I think there's a lot, the CIs are really large, and a lot of the performance improvements could have just been like the noise from using, let's say, a specific sort of random serial, things like that. Furthermore, a lot of the claimed improvements are actually not even improvements. So the ordering of algorithms here is if some other algorithm on the top claimed improvement over some algorithm below that. So for example, curl D2RL claimed improvement over curl. Similarly, Sunrise claimed improvement over, I think, DRQ, RAD, and curl. But you can clearly see that there is a lot of noise in its evaluation. Okay, so I think I showed a lot of results. Maybe back to the summary slide. So to summarize this talk, what I'm saying is we should use interval estimates as opposed to point estimates for reliable benchmarking. For qualitative summarization, performance profiles are a good way of doing things. We should ask the mean and median, or there are better aggregate performance measures from robust statistics such as IQM. I guess ideally we should report all these aggregate metrics. And maybe this is one of the most important points from this talk is we should provide individual runs for better statistical comparisons. So for all of these, what I really need is the scores for each of the individual runs. And at least for this work, what I had to do was I had to email about, I think, 10 to 15 authors to get the reported scores from their paper. But if, let's say, we provide these runs in addition to our code, if we just attach these runs in our GitHub repo or something, that will make life for people easier who want to do better statistical comparisons, even if you don't do that in your own work. And finally, as I said earlier, there's only a few lines of code for reliable evaluation. So I guess I left actually pretty much a lot of time for discussion. So happy to take any questions if you have any. Yeah, so Matt has raised a hand. I guess Matt, you can go.
First of all, thank you for the nice talk. A lot of us here do care a lot about this topic, so it was great to have you come out and talk to us about this. I looked at performance profiles a little bit, but then got confused about the way of combining tasks. So if you've got 29 Atari games, I think this makes sense. But if I'm doing, Mountain Car, Grid World, and Cart Pole, and StarCraft, does it? What happens when you have qualitatively? Because a lot of papers, they have 1 or 2 toy domains, or maybe 3 toy domains, and then a real domain. Can we do this kind of aggregation or evaluation across tasks if they're very different?
Yeah, so I guess that's an interesting question. The assumption was that you're doing a plotting this profile over a benchmark. So like, for example, as soon as we are able to report some sort of aggregate measure like mean and median, we are assuming that scores across different tasks are comparable. But the example, for example, you gave me, I think it is sort of apparent that, oh, Mountain Car is very, very different from StarCraft, and maybe we should have them as separate comparisons. So at least personally, it doesn't seem like that they should, because for example, think about normalization itself. Like for Atari games, we can just say, oh, we can normalize scores using humans and just report human normalized scores. It's unclear how would you make a normalization scheme so that it looks like the scores in StarCraft in a similar range as scores in, let's say, Mountain Car. Also, I guess the other question you're asking is, or saying is, the one task, or the StarCraft task is really, really much more difficult, and in some sense has much more value in terms of the result, as opposed to the toy tasks you have. So I do think aggregation there might be trickier, but then again, I guess you can aggregate things over the toy benchmarks represented. Like I think it's still fine to aggregate things over, let's say, Mountain Car and Cart Pole and other things like that, because they all look like similar domains or like similar scale domains, and you can make a case for why you can mix results across these benchmarks. Like at least, for example, the thing I'm saying is you can say, oh, mean performance across these 3 tasks is this. And I think no one would complain that why are you comparing or aggregating score across these 3 tasks? Does that answer? I guess it was a non-answer, but does that make sense?
Oh, and Andrew just dropped a reference in the chat. But yeah, I think that does make sense, especially since I could take those 3 toy benchmarks and run 1,000 trials, and in StarCraft, maybe I only have 5. So it would probably make sense to put those separately. Cool. Thank you. I'll let other people ask questions now.
Yeah.
If no one else is going to ask a question, I'll ask an unfair question. Can you hear me?
Yeah, I can hear you.
So I work a lot in survival prediction, which has sensor data. So you know the answers for certain individuals, but not for others. You have like a lower bound. Is there a way to take your ideas here and apply to situations where there's censoring in the values?
Sorry, actually your audio was chopping a little bit. Can you repeat your question?
Okay. What if you have a situation where over different trials, sometimes you have the answer for sure, and you have some evaluation measure. And sometimes you have like a lower bound on that. So again, one of my colleagues combinatorial questions. And sometimes he knows algorithm A does better because he can actually get the answers. And for some situations, algorithm A completed in 10 seconds, and algorithm B 3 hours. But we don't have the number, we just have a lower bound. And then it gets more complicated for multiple algorithms. We have lower bounds and you can't really compare them. This is very common survival prediction. Is there any way to extrapolate your ideas to this case where you have censored information, censored labels?
So I guess at least like, thinking about this a little bit, there is a naive way to apply at least performance profiles, because if we look at these performance profiles, they're really just caring about this binary random variable or binary indicator, whether a certain score is higher than a threshold or not. So let's say you know that your score is at least, I don't know, 10, right?
Yep.
So you have these values of these indicators for all the values greater than 10. Below 10, I guess you don't really have them. So you have to really remove that information. But I guess basically I'm saying, like, look at this graph. This graph goes from 0 to 2. Now, let's say you have the information that your score is above 0.25. So this information can be used in bulk of the profile after 0.25. Between 0 to 0.25, you really can't use that information because you don't know exactly where the score is. So there is a way to do this, which will be correct at least. But I don't know if that was something you're looking for. Now, if you can do this, if you can plot these profiles, then you can basically compute any of the metrics we have been also talking about. It's just that there is, in some sense, there's less data on some of the points, while more data on some other points. So maybe what I mean by that is, so if you look at each of the points in this profile, each of those points is an average of n times m numbers, which is basically n runs. You have m tasks and n runs. That's really what each point on the profile is computing. Now, in your case, I think what would happen is you don't have n times m points for each of the points. You have sometimes less points and sometimes more points, and that is still fine. And I guess once you're able to compute the profile, you're also able to compute any of the metrics like mean or median or whatnot.
Yeah.
Does that make sense?
Yeah. Again, it wasn't a fair question, but it was just kind of pre-associating what you're talking about. And this curve looks like this is what survival curves look like. It's 1 minus.
Yeah, so it's actually, yes, it's exactly so there is different names for this thing. So this is really the tail distribution, and this is also called the survival curve.
Yeah. Okay, well, good. I'll think more about it. But again, that was a wonderful talk, and I'm going to use it, some of those ideas in some of my classes as well. Wonderful, thank you.
Cool, thanks. I think someone has a hand raised. Yeah.
Yep. Thank you for the talk. It was an awesome talk. I find the subject is very interesting, to say the least. I had one question though about parameter, sensitivity. Because we use, a handful of hyperparameters that we have to tune to actually make things work. This is not visible often in papers, at least, and nor that it's not visible here neither, right? What do you think about parameter sensitivity and how we should be able to, evaluate this? And see because sometimes you would compare different algorithms, but with the same kind of default parameters on an environment, but maybe if you were to tweak them or to tune them, you would have better performance, for example. You see the idea, I guess.
Yeah, no, I see that. Yeah. So I guess this is actually a pretty important question. In this work, at least, we sort of sidestepped this, but we said, well, we assume you have the best hyperparameters you obtained through some tuning process, and then you're using them. That's what we're doing here. But I guess coming back to the question of, okay, it's possible that some method really requires a lot of tuning. while other method requires it's a little bit of tuning. And somehow this is not visible in these results. So the assumption, at least in this work, was everyone gets a fair tuning budget so that it's the same, so that we are not unfair. But let's assume you want to show this aspect of an algorithm too. One thing you can do easily would be just, I guess, if you have some way to come up with valid hyperparameter ranges for different methods, you can say, oh, I'll use 5 hyperparameter configurations for these 2 methods. And somehow I can say that these are valid configurations, because maybe that's also a difficult problem. But if you're able to do that, you can just mix the result from all these configurations in some sense. Because basically these are valid estimates of scores, right? You got for a different hyperparameter. And you can just say, oh, so you're asking basically a question of, okay, what if I was to change the hyperparameter? How would my result change in some sense? Now, there has to be some sort of reasonableness here, because if you just change, let's say, Adam's learning rate to 1, nothing would work. No one would care about that either. But as long as you can justify, oh, these hyperparameters are reasonable for this method, I think you can just, again, as I was saying, you can mix the result across all the basically hyperparameters and just report like these statistics there. And the variation now, or the sort of uncertainty you get, is also capturing the uncertainty coming from hyperparameter tuning. So if you have a really sensitive method, you'll see the CIs are really wide. But if you have a less sensitive method, the CIs would be small. And I guess same for, I guess maybe if you just plot the performance profile and go back to these things, you'll see actually the tails really increase, or there will be like the outliers would really be there. So it'll be visible clearly, at least in these profiles. But does that make sense?
Yes, it does. I'm going to take another step, I guess, on this and be a bit more, because this comes from the point of view where we actually try, to do science right. But the whole point of this talk is also to say that we don't in some way already. And it's exactly the same here. What prevents me to actually try to find the best hyperparameters first, and then to just sample a lot of runs with those best hyperparameters to hack my confidence interval and be better in terms of performance, to be, in front of the others in my paper. I'm stretching it out here, but you see the idea.
Yeah. So I guess one maybe simple answer would be, if you have a really important or difficult benchmark, which is expensive, like think about Atari. I don't think people are able to tune hyperparameters that extensively on Atari, because it is really expensive, especially if you're using the entire benchmark. So if you're using small scale benchmark, maybe you have this luxury. As soon as you go to a bigger benchmark, hyperparameter tuning ends up using a huge amount of compute. And I guess, at least at Google, I can say we don't really tune hyperparameters that much, because it is just too much effort for too little gains. But yeah, so I think this might have a self-correction effect, in the sense that as we go to harder and harder problems, hyperparameter tuning might decrease, and we'll just eventually naturally go towards methods which are more stable. Although this is not really an answer to your question, I guess, that I also know. But I guess there are two things. So you can say, this is something that I was alluding to earlier, which is the way we do things in supervised learning, that we have a separate set of validation and like testing. Similarly, in RL, we can have separate validation gains where we do some tuning for some amount of budget. And now, given the results, we just apply the hyperparameters to all the other gains. That is a valid protocol. And I think, at least on Atari, that's a reasonable protocol we follow if we use, let's say, 50 games. It's unclear what happens when you're only using 5 games and you're always tuning things on that and reporting results on that. That is something I think, I don't know how to fix that, at least.
Yeah, I was not expecting for a clear answer. It was just to, still pick a bit on the subject, because I love this subject and I think the work that you've done is awesome in that direction. But I still think that there is so much more that we can still try to do. And so just wanted to point that out.
Yeah, I don't think this work is tackling a single aspect of things. And there's like a tons of things you can do for improving evaluation. I think there's a tons of work left. Yeah, Matt, you have another question, I think.
Oh yeah, just actually following up on Matisse. So let's say performance, we all agree with you, performance profiles are the best way to evaluate RL algorithms. So then someone submits a paper and they don't use performance profiles. Do we try to get that paper rejected? Because the reason I was thinking about this, because you probably heard there's lies, damn lies, and statistics, right? You were showing that different algorithms could do better depending on what you're measuring. So if I'm an author trying to get my paper accepted, I'm going to pick the measurement that makes my new algorithm look the best. Is there anything we can do in reviewing to try to catch that, or do we need to insist that everyone use performance profiles?
Yeah, that's a pretty good question. So I guess maybe just upfront, I should say one size fits all probably wouldn't work, because I guess if you think about the role of empirical results in science, it's more about like justifying the story you have in your research, or like sort of adding evidence to whatever your research is. So let's say I've really like a break-tracking, like really like a phenomenal idea, and I just want to justify that it seems to do something interesting on these benchmarks. I think there I'm just looking for evidence that, oh, it sort of works. It doesn't have to beat everything out there yet. But let's say now this is one kind of paper. The other paper is saying, oh, I added this sort of trick to my loss, everything works better. This is really much more an empirical paper. And I think the standards there should be much higher too. So if it's more of a paper saying, really relying on, oh, my method is really better than whatever exists out there, then I think empirical rigor should be much more. And there, I think, I guess we should maybe, or at least promote, say, so again, maybe I can give you an example. So I guess if you look at Nurep's checklist, they say that we should report error bars, or at least they ask that, have you reported error bars? People are free to answer no there. Similarly, I think for evaluation, we can ask questions like, have you reported like a more thorough evaluation? And if people are free to answer no to that question, but I guess that will encourage some more people to report these things. Regarding picking metrics, I think it's on the authors to justify the aggregate metric they're using makes sense in their setting. For example, I guess I can tell you an example of a paper which said, okay, median is not the metric we care about. We really care about performance of the bottom 5% in some sense. And we really want to optimize this performance, because they're saying existing algorithms do well in median, but they're really performing badly on the bottom 5% of the game, things like that. So again, I guess, like same metric shouldn't work. But that said, if you have a big benchmark, I assume you're interested in some sort of overall or aggregate performance. And I guess in that sort of scenario, things like mean or having like a fixed metric makes sense, which is, that's why I think we end up using mean or median or things like IQM. But in addition to that, I think it's fine to report additional metrics which show what is the benefit your method presents over existing methods, even if it's not like good in these standardized metrics. So again, I think overall I want to say is the role of evaluation is to just add evidence to whatever story or method or idea you have. And I think it should just supplement things. We should only be careful about just doing a fair job or good job at it and not trying to conceal. Like, for example, let's say if I say my median is higher than your median, I guess the question we are asking is that really a true statement? Like, is there a lot of variability in your median? I think this is what we're trying about this. And now the question is, again, the thing is, as I said, median is really a specific way of measuring things. If I measure things differently, maybe things would be different. And often I think authors do not have the incentive to do that because they believe that reviewers might criticize it. But I guess if you're trying to do good science, I do think we should be more thorough in our evaluation. So it's easy to say, but there is, I think it is, finally, I think one more thing I want to say, the authors and the reviewers are the same community. So we can complain that authors are not doing good things, but they are also really the reviewers too. So it is on us as a community to just say, oh, let's all try to do things better than what we have done before.
Yeah, I like that. Let's do things better than before. I also liked your example of the bottom 5%, because I could see a research track where someone develops a new algorithm and it doesn't really work. Oh, wait, but it does really well on the worst runs aren't quite as bad. So then we can change our story to say we're optimizing the bottom 5%. And that sounds kind of cynical, but I think that's actually good science. I mean, if you set out to do one thing, but accomplish something else and can convince people it's interesting, that's still cool.
I think it's all about, as long as you can convince others and like yourself that this is actually reasonable thing to do, I think it's fine to report metrics. Yeah, so that's why I wouldn't say everyone should report things. I guess performance profiles are still like a reasonable thing to put in your appendix because they just tell you the entire story, even if they're not telling you the exact thing you're looking for. Plus, they are much better than tables because you can just squeeze this thing in a single plot. Tables just like never are going to be in your main paper, I think. So maybe one fun fact. So performance profiles are also recommended by the original Atari benchmark. I think they only did like the issue with these profiles is, I guess, the thing that the slide is showing that they will often intersect. And I think that makes things trickier. But I still think they have a lot of value because they can just tell you all the percentiles and other things, as I said, in a single shot. So you don't have to like really think about, okay, what are these metrics? Cool. Thanks. Anyone else have any thoughts, questions they want to ask? I guess not. Maybe we can end the talk in a couple of minutes if I don't get a question. It's almost time to.
Yeah, that's probably sufficient awkward silence. Oh, wait, did someone else? No. Well, cool. Well, thank you again for coming and giving this talk. You gave us a lot to think about, and we may end up pinging you with more questions.
Yeah. Feel free to ping me on email. Cool. Thanks.
Great.
Have a good day, everyone. Bye.